Here we are today for Unit 3B, putting numbers in perspective. So when we're working with large numbers or small numbers, it's often much easier to write them using scientific notation. So scientific notation is the format in which a number is expressed between 1 and 10 and multiplied by a power of 10. You can have 1 as your first number in your scientific notation. You cannot have 10. It needs to be a single digit. And then since we're multiplying by 10 and we are on a decimal system, deci meaning 10, that means all we are doing is moving a decimal back and forth. Okay. So if we take a couple of these, if we're going to go from scientific, or converting to scientific. Okay, so if I've got 3,042, we're going to move the decimal to come right after the first non-zero digit. And then from the power of 10, if it's positive, we're moving it to the right. If it's positive, we're moving to the left. Negative, we are going to the right. Another way to remember it is if it's a large number, it's going to be a positive value. If it's a small number, it's going to be a negative value. So if I have 3,042, we're going to move it 3 places to the left. And we're going to get 3.042 times 10 to the third. If I have 0.00012, the decimal is moving 4 places to the right, and we will end up with 1.2 times 10 to the negative fourth. And then if I have 226 times 10 squared, we're going to move it 2 digits to the left, which means our squared is going to become a fourth, and 2.26 times 10 to the fourth. If we're going to go from scientific notation to normal form, then we're going to move the decimal to the right if the power is positive, left if the power is negative. Once again, it's a little bit easier to remember. If it's a positive value, it's a large number. Negative values are small numbers. So if I have 4.01 times 10 to the second, I'm going to move it 2 places to the right and end up with 401. If I've got 3.6 times 10 to the 6th, we're going to move it 6 places to the right. And in this case, we're going to have to add zeros for all the places that we're going to add it. So 3, 6, and then 5 zeros after it, okay, for 3.6 million. And if I've got 5.7 times 10 to the negative 3, we're going to move it 3 places to the left. So after I move it to the 5, to the left of the 5, I got to move it 2 more places, which means I'm going to have to put 2 zeros in as placeholders. All right, so for example 1, we're going to rewrite these using scientific notations. So the total spending budget of the federal government was $3.9 trillion. And so we are going to convert that. We have to move the decimal 12 places. So then it becomes 3.9 times 10 to the 12th. Now, just a little side note, one of the nice things about these larger numbers is we put commas every 3 numbers. And so if you've got a large number like this, you can count the commas in groups of 3, and it'll save us some time. So for example, 3, 6, 9, 12. Okay, so every time there's a comma, it's a group of 3 for our scientific notation. For B, we don't have that luxury. The diameter of a hydrogen nucleus is approximately that. No commas on the decimal, so we're going to have to count. That is 15, because I need it to come to the right of the 1. So 1 times 10 to the negative 15th power. For 2, we are converting back from scientific notation. So 5.027 times 10 to the 1, we're going to move it 1 place. So it becomes 50.27. And for B, we have negative 3.89 times 10 to the negative 3. So we're going to move it 3 places to the left, which means we're going to need 2 zeros to put in this place. For those that like peanuts, Lucy's asking what are the chances that Schroeder and her are going to get married, and it's about a Google to 1. And how much is a Google? That is a 1 with 100 zeros after it. So he could have said 1 times 10 to the 100th, but, you know, sometimes you want to go a long way out just to sort of make a point. All right, with your calculators, you do have a couple options for these. Some calculators have a 10 to the x button. Some of them have an E. It would be a capital E. If you have a scientific calculator, it's going to be a capital E. If you have a graphing calculator, it's 2 E's, capital E, capital E. Okay, so make sure you're using the correct. So if I wanted to write 3.5 times 10 to the 6th, you could do 3.5 times 10 raised to the 6th power, or you could go 3.5 e to the 6th. It's the same value. Couple mistakes that people will make. If you put 10e6, thinking 10 and then exponent and 6, it's going to take 10 and then times it by your 10 to the 6th and throw you off by a factor of 10. So you do not need to put the 10 in there. If you want to look at it, for those with the graphing calculator, a couple different points, a couple of these out for you. This E up here with the sign, this is your programming E. Most of you will probably never touch that. Use that for when you're doing programming. If you want, here are your two options. Here's our 10 to the x. So if you would like to use 10 to the x, you can click that button. This capital E, that's the E they're talking about back here. Okay. So for scientific notation, you can either use this one or this one if you have a graphing calculator. All right, multiplying and dividing with scientific. If you need to multiply or divide, you're going to multiply the first numbers, and then you're going to add the exponents. And if you are dividing, you would divide the first numbers and then subtract the exponents. So if I have 6 times 10 to the 2nd times 4 times 10 to the 5th, well, 6 times 4 is 24. 10 squared times 10 to the 5th is 10 to the 7th. All we do is add the exponents. Notice we do have a small little issue with 24. It is not a single digit number between 1 and 10. So we're going to have to move the decimal place. And we get 2.4 times 10 to the 8th. If we're going to divide it, we're going to do a similar thing. So I'm going to divide 4.2 by 8.4. And then I'm going to subtract the exponent. So negative 2 minus a negative 5. So that gives us 1.5. 2 negatives make a positive, so 10 to the 3rd. Similar problem, 0.5 is not a single digit number between 1 and 10. So we're going to have to move the decimal, and we end up with 5 times 10 squared. All right, adding and subtracting, unfortunately, are not that easy. If you're going to add or subtract, you've got to put them into ordinary notation, solve it, and then plug them back in. Okay, so 3 times 10 to the 6 plus 5 times 10 squared. We're going to have to convert that to 3 million plus 500, get 3,500,000, and then convert that back into scientific notation. So 3.0005 times 10 to the 6th. Same thing with subtraction. 4.6 times 10 to the 9th, we're going to have to convert to 4.6 million. Oh, sorry, 4.6 billion. The 5 times 10 to the 8th is going to be 500 million. Subtract them to get 4.1 billion, which we then convert to 4.1 times 10 to the 9th. So it's a lot easier to multiply and divide with scientific notation. Adding and subtracting, unfortunately, no such shortcuts. All right. So if I want to take 6.97 times 10 cubed, and I want to multiply that by 2.34 times 10 to the 6th, I'm going to multiply the first numbers. So 6.97 times 2.34 is 16.3098. We're going to add the exponents. So 3 plus 6 is 9. 16 is not between 1 and 2. So we're going to move the decimal over, and it becomes 1.63098 times 10 to the 10th. For B, first thing we're going to do is we're going to divide 5.16 divided by 8.65. And this can give us 5.579. Negative 4 minus a negative 8 is positive 4. So our answer is 0.597 times 10 to the 4th. Unfortunately, that is once again not between 1 and 10, so we're going to move the decimal over 1 and get 5.97 times 10 to the 3rd. The other thing that's really nice about scientific notation is we can get a fairly close approximation fairly easily. So I'll have a lot of students that'll tell me, why do I need to know math? I can just plug it into the calculator. Well, how do you know when the calculator gives you a wrong answer? So this is one of those things that you can do to kind of make sure that your answer makes sense. Is it in approximately what you would expect? So if I wanted to multiply 5,797 times 326, well, I can round 5795 to 6,000, and we're going to round 326 down to 300. And 6 times 3 is 18, and we end up with 1,800,000. So our answer that we get should be somewhere around 1.8 million. The actual answer is 1,889,170. Okay, so it gave us kind of a good estimate, but more importantly, it gave us something that's close. Because I'll have students that, give me something, and I'm just like, that's not even close to what you should be expecting. So the question is always, does it make sense, and is it close to what you expect? For example, if you're a doctor and your excuse for a malpractice suit cannot be, well, the calculator told me to do it. You didn't realize you plugged it in wrong. If you screw up on a medicine or something like that. So you've got to be at least kind of conscious of what is a reasonable answer and what do we expect. All right. Perspective through estimation. So if I want to know how high is 1,000 feet? Well, 1,000 feet doesn't mean a whole lot. Okay, but if we want to talk about a building, a story on a building is about 10 feet. Okay. So that means 1,000-foot building is 1,000-foot building is about 100 stories. Okay, so it can kind of give you a reference. If you have been to Raleigh, those buildings are probably maybe 30 stories, 40 maybe tops. So 1,000 feet would be a couple, 2 to 3 times bigger than those buildings. So, it gives you a reference. You're like, oh wow, okay, that's about what I'm looking at. Once again, what do you expect to have happen, and what are you expecting the answer to be? Sometimes you can get kind of a broad range. If you're talking about a city, is there a population in the hundreds, the thousands, or the millions? If we're talking about Greenville, we're talking tens of thousands to, close to 100,000. Raleigh, Charlotte, you're talking, you're measuring things in the millions. If you're talking about population of the U.S., you're talking about hundreds of millions. So you can kind of get a reference for, just by the magnitude of something, what the answer is. So what order of magnitude estimates the amount of hours you sleep in a year? So if we say you sleep about 8 hours a day, and there are 365 days in the year, well, we could round 8 to 10 and 365 into the hundreds. So you were looking at somewhere in the thousands of hours slept a year. Okay, that would be your magnitude. And if you wanted an approximation, 10 times 400 is 4,000. So that's, since we rounded both of them up, 8 to 10 and 365 to 400, you're thinking, okay, so it should be close to 4,000, but it's going to be on the lesser end of what we actually get. And then another way is to do a comparison. So, $100 billion. Okay, it's a number that pops up. How big is that? So, if we want to convert 100 billion seconds into years, it kind of gives us a reference. We can convert seconds to minutes, minutes to hours, hours to days, days to years, times that by 10 to the 11th, and you are looking at 3,171 years. So that means if you counted a billion to a billion using $1 bills, 1 bill per second, it would take you 3 millennium to reach $100 billion. Okay, so it kind of gives you a reference. And that is assuming that you don't eat, you don't sleep, and you are not allowed to die while you're counting. All right, another one is to do it by scaling. So 1 centimeter represents 1 kilometer. You see these on maps. You'll see them on blueprints for houses, things like that. Okay, a scale just means that 1 centimeter is 1 kilometer in actual distance. You can do it with a mini ruler. You may have seen those on maps. Or sometimes you can do it as a ratio. Okay, for example, 100,000 centimeters is 1 kilometer. Okay, so it'd be 1 to 100,000. So these show up a lot with architects and engineers. You can see them with timelines. You may have seen like a time-lapse photo where maybe a second is equal to a minute, or a second to an hour over something with weather, or changes throughout the seasons. Some of you've seen those. Or kind of the other classic one you're starting to see now is speeding up cars, like driving down the freeway to show like a day to night transition on a TV show or a movie or something like that. Okay, those are just all ratios. So if you have 1 inch represents 1 mile, the ratio is 1 inches to 1 mile. And then if we're looking at the next one, if you have a map with 1 inch equals 30 miles, if 2 towns are separated on the map by 5 inches, what's the actual distance? Okay, most people would just go, oh, 5 times 30 equals 150. But if you just kind of show you how these work, since we've done a lot with converting units. So we have 5 inches. Our ratio, equivalence ratio, is 30 miles is 1 inch. Notice the inches cancel. The only unit left is miles. And so 5 times 30 miles is 150 miles.